Today we're going to be talking about the extreme value theorem. And if you have a continuous function on a closed interval, that function has both a maximum and minimum value on that interval. So let's look at a few possibilities that we have here. We have an absolute minimum here. I have no other y values that are smaller than that value. We have a local, where our derivative, and they have that slope of that tangent line there, drawn in, is 0. A local minimum. Again, derivative of the tangent line is 0. We have an absolute maximum, where our derivative technically there would be undefined, but it's still a point on our graph. And then we'd have a local minimum at an endpoint. So notice a few things. Absolute minimum occurred at one of the endpoints. And then we had some local values, and then we had an absolute value where it was the highest point along the interval. Sometimes the local minimum is going to occur, or an absolute minimum is going to occur at an endpoint, or it's going to occur somewhere in between. Now notice at each one of these points here, so here, f prime of x equals 0. Here, f prime of x again equals 0. Here, f prime of x was undefined. So that's a few key things that we need to know. Okay, local extreme values. So we have an interior point. A local value happens only if that function value, I'm sorry, a local maximum, only happens if that function value is greater than all of the surrounding y values. A local minimum happens only when that function value is less than the surrounding values. Okay, and then we have a local max or a local min at an endpoint if that same inequality holds true for all numbers less than or equal to that number. And we'll go through an example of that. Okay, so here for this example, we have two different cases, and then we have to tell whether or not it holds true for our extreme value theorem. So an absolute max, so look for your highest y value. My highest y value happens there at f of c. Absolute minimum, the smallest, that's here at f of d. Now locally, local max and local min, so our local values here, f of a would be considered a local min because it's smaller than the values around it. And here, f of b would be considered a local max because it is higher than all the points surrounding it. And yes, this holds true for our extreme value theorem because f of x is continuous on the interval. Okay, and that was a key thing from the extreme value theorem. Your function has to be continuous. Absolute max here in this case. So the highest value here would be at f of b. Absolute min would be here at f of a. Local max. In terms of the relations around it, you cannot call this a local max because, yeah, as you approach b, but our function value jumps up there. So we couldn't call that a local max. So I might say there would be no local max. One could debate that this f of b up here would be considered a local max, but I don't know if I'd call it that since we've already classified it as an absolute max. So I'm going to go with a none there. Local min, now our local mins, that would be f of c. And does their extreme value theorem? No. Our function f of x is not continuous. Okay, local extreme values. If a function has a local max or local min, it's going to happen when the derivative is 0 or at an endpoint. So what we're going to be doing is we're going to be finding the derivative and saying the derivative equal to 0. And then we're also going to be looking at the endpoints and finding those function values. So our first example here. In this example, we need to find the extreme values of the function on the interval where they occur, identify any critical points that are not stationary points. And this is very typical of a question that you're going to be seeing a lot on the AP Calculus exam. So I want to make sure you guys understand this one. Okay, so extreme values happen at either a critical point, so when your first derivative equals 0 or is undefined, or at one of the endpoints. So I have to find the derivative of this function. And remember, you find critical points by setting the derivative equal to 0 and solving 3x and x minus 2. So our critical points happen at 0 and at 2. Okay. Since these are both stationary points, since that's when the derivative equals 0, polynomial is always defined, so I have no critical points that are not stationary points. Remember, stationary points are when the derivative equals 0. So now we need to figure out at these critical points or the endpoints which is the highest value, which one is the lowest value. So you actually evaluate the function at the endpoints and any of the critical points. And you guys don't need to go through that. You don't need me to show you how to do that. I have that calculated. And we have, this is 1/8. F of 0 is 1. F of 2 is -3. And F of, or H, I'm sorry, H. In my notes I have this as F of X is 17. I apologize. I know it's the function H. In my notes I have it as F of X, but I changed it on this example. Okay, so we need to find the extreme values. So we need to find the absolute min, so the absolute smallest number, and that's what this is. And then the absolute max, the absolute highest number, is that number. And then we are done. Okay, our next example. Again, finding our derivative. Setting that derivative equal to 0. Now in this case, our derivative's never going to equal 0 because the top can't equal 0, so then we need to look at when the derivative is undefined. Our derivative is undefined. That's a 2. When that denominator equals 0, and that's going to happen at 0. And this is where f prime of x was undefined. So now we test our points in the original function. Test your two endpoints, and you test h of 0. Now h of 0, this was a critical point, but not a stationary point, just because our stationary point is only when the derivative equals 0. We didn't have any of those. So the critical point happens when you have your derivative equal to 0 or is undefined. So plugging in h of -2, we have -2 to the 3/5 power. Again, I use my calculator then to find that value. That ends up being a min. Because I'm negative, I know that these values, when I plug them in, are going to give me a positive number. And then 3 to the 3/5. This one's 0. I know this is some positive number, some 1.93. So this would be a max. Okay, our last example talks about, now I'm finding critical points, but I don't have an interval. But let's look at the domain of this function. I can plug in any x's there, but for here, my domain is restricted from -8 to 8 because I cannot take, if I plugged in -9, I would have 64 minus 81, and that would give me a negative under my radical, and we're only going to be dealing with real numbers in this in calculus. Okay, so I find my derivative. And we have a product rule happening here. Okay, so now we have that function. So that's our derivative. Let's simplify that derivative a little bit. We would have a minus, oh, I forgot a 1/2 in here. I just realized that. I forgot to bring down my exponent because the 1/2 and the 2 cancels. I was kind of looking for those to cancel and they didn't. Okay, so now I get my common denominator, so I multiply this function here by root 64 over root 64, and I do some more simplification on the bottom. I don't multiply it. I multiply it by 64 minus x squared, the square root of 64 minus x squared. So I multiply that on the top and bottom, so that cancels that out. And going through some simplification, I'm not going to bore you guys with that algebra because the video is getting semi-long enough already. You get this function that you might want to try and simplify on your own just to confirm that you get that function. So now let's look at this. Okay, you set your top equal. That is where you're just going to have a stationary point. And this happens by subtract the 320 over, divide by -10, at plus or minus 4 root 2. You set your bottom equal to 0, and that gets you the points where you are critical, where your denominator is undefined, and that's positive or -8. But I already knew that from my domain restriction. So now what I have to do is I have to find f of -8, f of -4 root 2, f of 4 root 2, and f of 8. And so now you're plugging all of these in. And when I'm plugging f of 8 in here, we end up getting a 0. I'm sorry, f of -8, because I get 64 minus 64, which happens to be 0. You get the same thing when you plug in a positive 8. For -4 root 2, we plug in -4 root 2. That's a -20 root 2, because I multiply the 4 times the 5. And then underneath the radical, we get a root 32, which that simplifies to be a 160. When I plug in a positive 4 root 2, I get 20 root 2 times by the square root of 32. This happens to be negative now. Get with the program. This is a positive 160. So now you have to look and see. This is my smallest value, so this is going to be my minimum. This is my largest value. That's going to be our maximum.